some new, there are some new participants, so it is a continuation of the course which Vladimir gave in the scholarly algebra. Vladimir Dotsenko is professor of Strasbourg University, visiting us last week here.
All right. So it's really task because it's first of all, even people who attended for example, E of 1, 2 is a one-dimensional vector space which is just spanned by the span of the bracket of x1 and x2, and the E of 1, 2, 3 is two-dimensional, so it has many different polynomials, but using the anti-symmetry and the Chicago identity, you can choose a basis. And of course, that's one possible example to which we return several. Now, just to tell you about shuffle operands on the same word for race. So somehow, so there is another whose objects are just sequences. So somehow you can say just this is a non-negatively graded vector, right? So and there is, well, okay, the vector non-negatively graded vector spaces are simple enough. So what I'm going to say now might look completely absurd. I'm going to make to write for you an equivalent category which is much more complicated at first glance. So this category is what we would call ordered linear spaces. And somehow these are functors from the category that I'm going to go toward maybe into that. And these are finite, totally ordered sets, and the morphisms are order preserving bijection. Of course, if you have two totally ordered finite sets, between them you either have no order preserving bijection, just one. So it's a very stupid category. Between any two objects, you have either one, either the only isomorphism or no morphism at all. But wait for a second, you will see why this category is very useful. And let me reproduce now a very similar formula for right now an monoidal structure in the category ordered linear spaces. So now, well, actually, this is good. This is then going to keep this formula for the unit. It actually will work in both categories because here for one element sets there are no symmetries. So this is a lovely formula that kind of belongs to both worlds. But let me now write for you the monoidal. So now here, so these are ordered spaces. So I'll start as before. Of course, I can write that because integers from 1 to n have their order coming from the integers, so I can view it as a finite ordered set. Now, the tensor product will be over the ground field. This no longer has any model structure, so I have no right to do something like that. And now, I'm going to write something. So f from I surjective to integers from 1 to n. So I'm going to reproduce the same inverse of 1.
You mean subjective maintaining order?
No, any surjective map with the following condition that I'm going to write now, the only order that I'm going to care about is that the minimal elements of the preimages are in order. So minimum of the first preimage is less than the minimum of the second preimage, is less than the minimum of the last preimage. So, for example, let me I'll release this. So a typical so we'll still have this kind of pictures as before, which will actually draw these connections and think of some kind of combinatorics and all. But so, for example, what I can do, I can, so this is some element L, some element G1, 2. So this is kind of the allowed combinatorial type of, so I have this surjection from 1, 2, 3, 4 to 1, 2, where 1 and 3 go to 1, and 2 and 4 go to 2, and indeed the minimum of preimages increase from left to right. So everything. And the main property of this picture, of this goes as follows. So there is a gentle function from linear species to ordered linear species. And that comes from the forgetful function from the category word to the category fin. So if you have an ordered finite set, you can forget the order and get just a finite set. I think that in lecture to Shiva, I put some letter F to know, but then I realized that I very often use F for surjection, so in notes, I use the letter U for underlying finite set or ordered set. And then somehow you can associate to a linear species F and new ordered linear species FU, which relate to a finite ordered set I. You compute F on I without the order. So it's, functions there are like functions. So we have a function between these two categories. So we have the pullback thing for development functions. And if you think about this datum, it's literally just getting the symmetrical actions going from collections of elements to collections of vector spaces.
You will time, but it would be interesting to see, for instance, if F is Lie,
Yes.
and G, for instance, John, what is the difference of this?
Okay, so let me give you one. So we will see some examples of similar sorts towards the end of this lecture. Don't worry. So the main property, first of all, the main property of the forgetful is the following. Suppose that F and G are two linear species, and G is what is called reduced, meaning that it vanishes on the empty set. In principle, we have all possible finite sets, including the empty sets, and all that G vanishes on the empty set. But then,
they use not this condition.
yes.
What nothing about one.
No, no, absolutely nothing. Then you can take the composite. Oh, sorry. I did something very stupid. I closed the thing by saying circle, and here I will put the Russian letter sh for shuffle composite product. So you can take the composite product of F and G, two-year species, the composite product is defined, and then you can get the symmetries, you get an order of two-year species. Or you can first get the symmetries and take the shuffle composite. So you can do two different things. Turns out that as for clear species, they have one. And that is at the heart of everything we're going to do today, tomorrow, the day after. This kind of remarkable it's somehow it's not a very difficult task. So first of all, because G is reduced, this means that you can focus on not all maps but all surjective maps. Because somehow for maps which are not surjective, one of the pre-images will be 0, and so the corresponding term will be absent. Additionally, we want to remove the symmetric group here. And for that, you see that this huge direct sum, if the species is reduced, this huge direct sum is a free module over the symmetric group permuting the factors. And if your set I is ordered, then you can impose this condition on E by increasing from left to right, and this gives you a vector space of generators of that free module. So you can cancel the symmetric. So this is not a very complicated proof. It's just you need to state, figure out that this statement is true. And then once you know it, the proof is quite clear. Now, so operands are modeled in a circular category, so in the category of linear species with composite product. And the shuffle operands are modeled in the category of reduced ordered linear species with the shuffle composite product. These are the definitions of these two. And of course, you know, for this result, for this property to hold, we only need to get confused. But if we talk about monoids, we want to compose a linear species with itself. We want to have a map from A, circle A to A. So if we want one of them to be reduced, then yeah. So this imposes a very important constraint, which is a little bit annoying, but still not a big deal for many purposes. So, the constraint that we have is that if there's some white like this, the constraint is that we will generally consider varieties of algebras without confidence in the signature, because confidence is precisely what lives in what will be assigned to the empty set. So work with varieties of algebras without confidence. In other words, moving from operands to shuffle operands is not going to be a good idea where you want to encode, for example, unit or associative algorithms. Having a unit is not quite good for the signature. We're not going to use shuffle operands for unit algorithms. Or, thankfully, there are many interesting motivating examples of varieties of algebras without constants where there are interesting problems. So it's not going to be too profound for us. Now let me erase something. Let me erase. We're going to this. Okay, so this is the reminder of things that were said in the And now let me start talking about one possible, so first possible application. And as we are going to move to, some, I'll create some general context and we'll move to examples. So hopefully some things will become sufficiently clear. This first application concerns the notion that was introduced around about 10 years ago in a paper of Ivan Pavlovich with Mikhailov, the notion of a PW pair of varieties. So this notion is related to the notion of a functor of change and multiplication. And let me start with that. So first of all, let me give you a couple of examples and I'll give you the general definition. So there is a very well-known functor from associative algebras to the algebras. Take algebra A and consider the algebra A minus A, the same vector space with the operation AB minus B. There is a similar functor to Morgan algebras, where you take the A plus, AB plus, the operation AB plus. There is also, so perhaps I should also mention the example which I like a lot. So there is a variety of pretty algebras, so right symmetric algebras, which is symmetric in the last two arguments. And if you take the operation the algebra A minus, the same algebra operation A minus BA is true. And this you can make going further, take all to be admissible, perhaps I also write be admissible. The same A minus. But then somehow there are some more complicated situations. So for example, to each Lie algebra, you can associate what is called the Lie triple system. So an algebra with a triangular operation that satisfies some identities. So Lie algebra is functor into Lie triple systems where somehow we have an operation ABC, which is equal to something like that. And this operation satisfies so it's this operation always is symmetric. This operation is symmetric in A and B, and it satisfies some other properties. But in any case, so it's a variety. So it's and all of these are examples of a function of change and multiplication, meaning that you start with some variety, which is, so you start taking out, which is space with some operations, and define new operations using some combinations of the existing operations. So you find a minus a, b plus b, this kind of thing, and so on and so forth. So in general, so it's functions of change and multiplication are something like that. And perhaps I should say that in terms of operands, if V is a variety corresponding to operand P, so by this I mean that P is, it's like in that example of E. So if you have a variety, you can define a linear species P, where P of I is the multilinear operations with inputs indexed by I. And then you can substitute them into one another, so you have a monoid in the category of linear species. And a W is a variety corresponding to an operand Q, then a multiplication changing functor from the V algebras to W algebras is the same as a morphism of operands from Q to, so the node is the change of direction of the arrow. So, for example, to make it clear why it is the case, so we have this first functor that associates.
You mean on the way?
No, it's just there are no functors here. It's just I'm saying that to define a multiplication changing functor is equivalent to defining a morphism of functors in the other direction. So for example, there is this function from associative algebras to LieJor. I claim that it's the same. As a morphism of operands from Lie to us, because we can take the Lie bracket, which is the structure operation of the algorithms, and we can send it to the operation x1, x2 minus x2, x1. So algebras go in one direction, operations go in the other direction. So this is a perfectly valid thing. In the other direction, you don't really have a map. Since the fact that the operation AB minus BA satisfies the Jacobi identity means that this map from the operand B to the operand of associative algebras is a well-defined operand morphism with respect to the only relation that we have on the. Very good. So now there is, so in the case of associative algebras and Lie algebras, we can talk about universal developing algebras. So somehow we can, formally we can talk about the left adjoint functor, the functor of change of so the universal developing V algebra of an W algebra construction of OL is the left point of functor change. which means what? That you take, you can, in general, you can construct explicitly in the same way you construct the universal enveloping algebra, associative algebra, algebra. You say that, okay, you take the free B algebra generated by given algebra A and impose the relation saying that the operations that we can already express, we can compute on the level of the W. So this is, so now let me say, we tell the very same thing in the operatic. You will see how all these monoid instructions can be actually quite helpful to write some elegant compact forms. So in terms of operands, so we have a map of operands from Q to P, and then we're going to say the same to the following. So if A is W, then I define the species, let me call it epsilon A. So I'm, for the moment, I'm still in the category of linear species. So the species I'm going to define now is very much not reduced. Even worse, it's completely concentrated on the empty set. So it is going to be a very non-reduced. So a species, linear species M A, by the following formula, A of I is equal to 0 if I is not empty, and A if I is the empty set. What is the advantage of the advantage of this is that follows. And algebra structure and double algebra structure on A is the same, and left U-module structure on epsilon A. And so this means that by left module, I mean something that I express categorically in terms of the monoid structure. So I'm going to take the composition Q of EA to EA, satisfying conditions that Q circle EA, we can compute in two different ways. And this diagram, so we can compute it either using the composition in the opera or this arrow, or you can compute it using the action, module action. And the reason for it is that if you write the formula for the composite product where the second species is pointing on the empty set, this just means that you need to fill all the slots of the operation with elements of A, and so you get precisely an algebra structure. So it's not a very surprising result, it's just you carefully unwrap the definitions. It's an excellent opportunity to get used to all these definitions, but this is what you do. And now, we have a double algebra A, and I'm saying that universal enveloping algebra of the algebra of A can be expressed in a very compact way as follows. Now, what does this formula mean? I added this subscript Q, so I need to explain what this means. So the composite product is monoidal structure. In the category of vector spaces, if you have, for example, a right module and a left module over the same associative algebra, you can take their tensor product over and out. It's a certain co-equalizer to speak about it. In any case, it's a certain quotient of the usual tensor product. Here you can do exactly the same. So we already established that EA is a left Q module, and P has a structure of a right Q module, because we have a morphism of operands of Q to P. When we have a morphism of associative algebras, then the target becomes even a bimodule over the source. So, of course, you can do this. So this formula at least makes sense. We take the composite product of a right Q module and the left Q module, and I want to convince you that this formula actually computes the universal enveloping algebra. So if we erase Q, the composite product of P with EA is just the free P algebra generated by A. What does this composite product of Q do? It precisely says that if we have some operation on A, which can be some operation from P, which can be expressed, if we have some operation in P that comes from Q, we can already compute it on our algebra A. And so it's precisely the universal enveloping algebra I've been talking about. Okay. We have a good chance to see the key result that I wanted to give today. So I need to recall the notion of okay. So far, I talked in general about functions of change of multiplications and universal enveloping. Now, on U of A, we always have a filtration, which is very similar to the case of associative and G, right? On the universal enveloping associative algebra, on the algebra of filtration, and the relations are quadratic linear. We say that AB minus BA is equal to the bracket of A and B. So we have the quadratic element is equal to the linear element. Then, when we take the associated gradient, you have, according to the Poincaré Birkhoff Witt theorem, the symmetric. And here you also have filtration from ends and a surjective map from the universal enveloping algebra of the algebra that I'm going to denote A0. It's the same vector space, but with the zero operations. You have a surjective map to the associated gradient of the universal enveloping. And somehow this datum is called a PW pair if this map is always an isomorphism. So essentially, this gives you some kind of so a PW pair is this kind of situation in the function of change multiplication, where the universal algebra, roughly speaking, as a vector space looks the same regardless of what your operations are. it always looks at the vector space as the universal envelope of the algebra with zero operations. So there is of course a little bit more, because saying that two vector spaces are isomorphic, it's not really a very big deal, because in most examples we are talking about two vector spaces. For example, if we start with finitely many generators, the two vector spaces are just two vector spaces of countable dimension of the ground field. Of course, they are isomorphic. Just say that they are isomorphic is not so much. But here we actually say that there is somehow a concrete isomorphism between one and the associated gradient of the other. Well, associated gradient, it's so let me modify this definition. So this definition, this is the definition of Mikhailov and Shestakov from 2013. Let me slightly modify this definition and then explain to you how to obtain something interesting out of that very slightly modified. So, PPW pair in the way I'm going to think about it in the remaining few minutes of this lecture is the following. There exists an n function z from the vector spaces to vector spaces such that the underlying vector space of U of A is isomorphic to Z of A. Now I need to say isomorphic like as what in with respect. So functors with respect to morphisms of W algebras. With respect to W algebra morphisms. So you choose an isomorphism from U of A with Z of A and U of B with Z of B. Now, if you have any map from A to B, any map of W algebras, you have a map from the universal developing algebra of A to the universal algebra of B, because the universal envelope is a function. Also, you have a map from Z of A to Z of B, because an algebra morphism is in particular a linear map. And you want this diagram to commute. So somehow you want your isomorphisms to be chosen in some coherent way. And the main result about the developing pairs let phi from Q to P be a morphism of operands. And then for the corresponding varieties, D and double before the Q double pair, if and only if, and I emphasize it's an if and only if result. If and only if P the right module action of Q on these factors. So recall that Q and P are operands, so associated algebras in certain category. So because you have a morphism from you send an element of Q to P, you get an of P, find that substitute compose in the operator. And this is the result. Now, why this result is useful? Yeah, so why useful? Because if Q and P are reduced, if Q and P don't, if our varieties don't have constants, if the corresponding operas are reduced, then P is a free Q module, right? Q module, if and only if the corresponding shuffle opera is a free module, free right module over the corresponding shuffle. So this result is enough to check on the level of shuffle operas. And this requires some argument. It's not immediately obvious because on the level of shuffle operas, if you can somehow find generators, free generators of the module, no one told you that you can lift them magically to things which are compatible with symmetric. Something that you need to check. But, well, okay. Freeness of a module, in particular in this funny category, is something that you can check logically. That somehow, so for example, in the case of usual associative algebras, let's say graded, or possibly graded associative algebras and modules, you can somehow, you can compute the, if your algebra is graded, you have the obvious augmentation, and you can say that the module is free, even only if the Tor between the augmentation module and the module vanishes in positive. So this is an old result, and you have a similar result in the case of operas, because somehow here the role of grading is played by the number of inputs, by the arbitrary ratio, so we don't need to assume too much. Everything kind of is already set up nicely. And then in the universe of operas, you can actually operas, and so you can use the machinery of global basis for operas of normal forms and so on to establish freeness of a module, and this question suddenly becomes much more simple, much more concrete. So to finish with a couple of examples, of course, if you take an associative algebras and Lie algebras, you can reprove the classical result, but you can reprove it in case of characteristic zero. And in positive characteristic, on the contrary, you find that the corresponding thing is not free module, which tells you that even though in the context proposed by in the paper of Mikhailov and Shestakov, of course, pedagogical criterion works in characteristics. In positive characteristic, the associated graded is isomorphic to the universal analog of multiplication. You pass to associated grading. You cannot choose isomorphisms of vector spaces completely from target. So there is some little difference between these two approaches. So somehow I require some extra materiality, which is not required in the work of vector support. So somehow this passage to associated graded, it's not a between characteristic zero, but in positive characteristic, it requires choosing some splittings that you cannot choose in the combinatorial way. So somehow, using this result, you can also show that something cannot be done in a combinatorial way. Kind of. You can also use this result proved that the pair pre and G is a UW pair. This is a new result. It was not known prior to this work. And I say that this result of today is my so essentially, I think that the upshot is that for all currently known examples of PW pairs, this result shows that, in fact, the PW pairs are in stronger functorial sense, and there are some new examples. So our motivation, so we somehow, I don't have time to talk about this, so there is a structure introduced by Jean-Louis Ladé called demiform algebras. And Ladé asked some 15 years ago, so whether, so there is, so it's, they are related by a function of change of multiplications and multiplication, and Ladé asked if there is a PW type pair for this pair of varieties. And that remained an open question, and then using our result, we managed to prove this, which is this is already pre-E, it's something that you can sort of do by hand for dendriform form of the argument is already much more intricate, but using shuffle operas and combinations for operas, you can, and then this result you can actually show that this works. And this is as was I certainly should stop now, and yeah, we'll continue more of it. Okay, that's thanks. Any questions? No questions?